Welcome to the conclusion of Forensic Toxicology Chapter 8, Immunoassays, conclusion of this chapter. Here's a nice photograph of Malibu, California. Great photograph. Spectacular achievement is always preceded by unspectacular preparation. That's very true. Bobby Knight, famous basketball coach, said that. Now that we've discussed the 6 major types of immunoassays commonly used in forensic toxicology for drug screening, let's conclude with a short discussion of other issues that are vital to the proper use of immunoassays. Of course, on this slide it says quality control, a very important area. Solutions used for calibration and quality control should be in a matrix similar to actual samples that are going to be analyzed. This is significant because matrix effects can be large. Human urine that is used to prepare calibrators should not be more than 50% diluted. Controls must be prepared in actual human urine. If the immunoassay is a screening test, then a single calibrator is sufficient. For quantitative tests, multiple calibrators with concentrations that bracket those of the sample should be included in each assay. In other words, the concentrations of the samples need to be reflected in the concentration of the known samples that are going to be used to do a calibration curve. There should be control solutions run with the samples to show that the method can discriminate above and below the cutoff for screening tests. We'll talk about cutoff in just a minute. Prior to using the immunoassay, the lab should establish and verify a limited detection and linear range for the method, which is always done for any analytical technique used in a laboratory. Cross-reactivities to common interfering substances must be verified and understood before a method can be put into routine use. Okay, let's talk about cutoffs. Cutoff. This is a term used in screening assays because these screening methods identify samples as either positive or negative with no quantitation. Cutoff is the concentration of drug below which all specimens are considered to be negative. This can be the limited detection or a higher concentration. Usually there are administrative cutoffs well above the limit of detection set by organizations doing drug screening on their employees, such as the DoD, as we'll see on the next slide, the Department of Defense. If this concentration or higher is measured in a sample, then the sample is screened positive. Notice that all the immuno cutoffs are nanograms per milliliter, very low concentrations. Samples that are screened positive must be confirmed by GC mass spec in the Department of Defense program. Immunoassays have wide applications in most postpartum investigations, workplace drug testing, and human performance investigations. Analytically, urine is the specimen of choice for immunoassay screening because it has fewer interfering proteins and decomposition products. However, it is easier to relate impaired performance to drug concentrations that are measured in blood, serum, or plasma than in urine. An elevated blood concentration of a drug indicates more recent use of the drug. Be that as it may, urine is easier to use in a screening program since it is easier to obtain and is easier to analyze. Also, many drugs and their metabolites will be excreted into the urine days after absorption into the body has occurred. Here is a list of several common problems with immunoassays dealing with false positives and false negatives. Postmortem blood decomposes with time, producing biogenic amines. These biogenic amines cross-react with the antibody and amphetamines immunoassays and produce false positive results. Number 2, the second, salts in bile, some which will fluoresce, can cause false positives in the FPIA type of immunoassay. Number 3, since RIA and ELISA assays will give false positive cannabinoid results in old blood. Number 4, high concentrations of diphenhydramine cause false positive results in some urine PCP immunoassays. And 5, the fifth on the list, dihydrocodeine and codeine give false positive results in most morphine assays. Number 6, the last, enzyme-based assays may yield false negative results if the common preservatives, sodium fluoride or sodium trinitrogen, are present in the sample. This is a slide listing special problems that have been encountered with immunoassays over the years. For example, manufacturers of immunoassay kits for amphetamine strive to make kits that only identify amphetamine and methamphetamine in a donor's urine with a single immunoassay and exclude other amines such as over-the-counter cold medication, pseudoephedrine. They also want to only identify the D isomer. This presents a problem since the more specific an antibody is to D-amphetamine, the less specific it is for D-methamphetamine. The Roche online amphetamine method tries to solve this problem by using a mixture of two specific antibodies. However, this introduces an analytical problem. The methamphetamine antibody binds methamphetamine in a sample more strongly than the labeled amphetamine, and this binding difference may increase cooperative binding that we're going to see on the next slide. These assays are good screening methods, but the characteristics of their plots complicate interpretation of the assay results. A second problem, and another special problem of immunoassays, involves cross-reactivity studies. Although interfering substances have been identified, the metabolites of the interfering substances have not been studied, and they often also cause cross-reactivity. There are cutoff problems also. Administrative cutoffs for assays presents a special problem. Different immunoassays have different cross-reactivities to common metabolites of the target drug. For some urine samples, one manufacturer's assay may be negative and another positive, even if both have the same cutoff for the target drug. So over the years, immunoassays have, in general, been manufactured to be more specific to address this problem. Here is the typical cooperative binding curve, and you can see the assay response is right here, and if we presented 100% amphetamine to this assay, we'd get this response. If we presented 100% methamphetamine, we'd get a similar response. However, if we have a sample that has 75%, 25%, or even here 50-50 of amphetamine and methamphetamine, we get a higher response. The assay shows greatest response when amphetamine and methamphetamine are in the same concentrations. Ideally, the curve should be flat if cooperative binding did not occur. As you can see, when both amphetamine and meth are present, they are increasing each other's affinity for binding to their respective antibodies. This is still a good screening method, but the plot complicates the interpretation of the assay results, especially in quantifying the concentration of amphetamine and methamphetamine that's present in the sample. And lastly, as we conclude this chapter on immunoassays, in conclusions, immunoassays in forensic toxicology are used primarily to screen biological samples for the presence of drugs and similar toxicants. Many commercial kits are available. Each kit contains an antibody reagent, labeled drug, calibrators, and controls. Kits are very sensitive. Most immunoassays differ by the labeled antigen used and the method of detecting it, as we went through the 6 major types. Many methods can be easily adapted to automated analyzers. Cross-reactivity of structurally similar substances is a major problem with immunoassays, resulting in false positive results. Immunoassay results must be confirmed by a method based on a different scientific principle, such as GC mass spec. Thank you very much. This is the conclusions of this chapter.